Magnetism is one of the most useful physical phenomena and has been for centuries. Since antiquity, explorers have used magnetized needles to navigate their way across the globe. And even before then, animal magnetism, not like that, magnetoreception, has enabled animals like the homing pigeon to find their way back to their nests across miles of unfamiliar landscape. So, let's talk about magnetism. Today, as well as for navigation, magnetism is used in salvage operations, hospitals, metalworking, chemistry, music, and finance. In fact, the microphone we're using to record me and the speakers you're using to listen to me are all magnetic devices. And if for some reason you're watching this on a cathode ray television, say if you've been kidnapped by mad pensioners, you're also using magnets to watch me, instead of trying to escape, which is what you should be doing. Now, you're probably already familiar with the basic principles of magnetism, but just in case, magnets have two poles, a north and a south. Similar poles repel, whilst opposite poles attract. These effects are the results of the magnetic fields which every magnet produces, and which can be handily visualized with field lines like this. You may remember from science class that these lines represent the direction a tiny magnet would face if it were placed at that point and allowed to rotate freely. And you may also have heard terms like paramagnetism and diamagnetism, but we don't have time to talk about them in this video. Instead, we're going to ask questions like, does every magnet have two poles? Could you have an object with only one magnetic pole, a monopole, if you will? Well, what if you cut a magnet in half? This question was actually posed and answered back in 1600 by English physicist William Gilbert, who showed that if you cut a magnet in half, what you're left with is two magnets, each with two poles.
Wait, so where'd those extra poles come from?
I'm glad you asked, my stupid American friend. I'm kidding. We're not friends. Gilbert actually proposed that the field lines we saw earlier continue through the metal to form loops. So no matter how you cut the magnet, you always end up with two magnets. You never have magnetic field lines coming out of or going into a point, as you do with electric field.
So there's no monopoles then? Also, I'm Canadian.
Well, they might be possible, but in all the centuries we've studied magnetism, they've never been observed. Anyway, flash forward to 1831 and Michael Faraday, whilst working on one of his many revolutionary papers, noticed this circular nature and encapsulated it with the statement, "The magnetic flux through a closed surface is always zero," a statement James Clerk Maxwell later formulated into these two equations. In order to understand these equations, we first have to understand flux. The best way to understand flux is to return to the field lines we showed earlier and imagine drawing a line in space. The flux through that line is essentially equivalent to the number of field lines that pass through it. But Faraday mentioned a closed surface, and for that we need to consider net flux. Instead of a line, we now draw a circle. Once again, we count the lines passing through, but this time we subtract the lines going into the circle and add the lines coming out, giving us the net flux. For clarity, and because that joke is already getting old, we'll call this the enclosed flux. Note that you don't have to use a circle here. As long as there aren't any gaps, this definition will work for any shape, even 3D shapes like a sphere or a box. Both the equations we saw earlier are just different ways of doing what we've just described, counting the field lines through a closed surface, but in a more rigorous and mathematical way. The first one is what we call a surface integral. You've probably already seen line integrals in maths class. They calculate the accumulated effect of a function along a line. A surface integral is similar, except instead of along a line, as the name suggests, it integrates across a surface, with this loop here indicating that the surface we use must be closed. Since this equals zero, the accumulated effect of the field around the surface must also come to zero, which is just another way of saying that all the field lines which go in must come out, and vice versa. The divergence of a field is a measure of how that field expands or compresses at a given point. This terminology may seem a bit confusing when talking about magnetism, so think of it like this. If the field is expanding, that means the field lines are pointing away from that point. If the field is compressing, the field lines are pointing towards that point. Expansion equals positive divergence, compression equals negative divergence, and if neither are occurring, the divergence equals zero. Let's consider electric fields for a moment. There, the field lines always come out of positive charges and go into negative charges. Depending on how many of each charge are present, an electric field might have either positive or negative divergence, but it probably won't be zero. In magnetic fields, on the other hand, the divergence is always zero, meaning the field lines go in circles, never pointing towards or away from any one place. Every field line that goes into a point must come out of that point. As you may be able to tell from how much I started to repeat myself, seriously, who wrote this?
You did.
Shut up. These equations are essentially equivalent. They both say the same thing, namely that the enclosed magnetic flux will always be zero and that magnetic field lines are always circular. So, while monopoles could exist, they have never been observed. And for now, no matter how you slice it, a magnet always has two poles.